Alright, welcome to today's lesson on cubics in toilet paper form. Turning point form. Right, so you might remember that quadratics had this for turning point form. Alright, hopefully wouldn't surprise you all to learn that cubics have the same form, but written with a cube power instead. Now what that looks like is it looks like this. So you have your axes. All right, now I'm going to go through and pretty much talk about a table of values here, so bear with me. All right, so for x equals 0, you can see that given that k would be 0 and a would be 1, which would be looking like this, and h is 0 as well, so the most basic one is x cubed. For x equals 0, it's 0. For x equals 1, it's 1. For x equals minus 1, it's minus 1. All right, but it's not a straight line. All right, so the reason this is because you have to go and look at what happens to the fractions. So for 0, it was 0. For minus 1, it was minus 1. And for 1, it was 1. But it doesn't tell you the right story. So I'm going to go and erase this straight line here. We can put the 0 point, the 1 point, and the 1 point back. All right, let's have a look at what happens to minus a half. Now, minus a half being the x value, minus a half cubed is minus 1/8, because 2 cubed is 8. What about minus a quarter? Minus a quarter cubed is minus 1/64. So as this fraction is getting smaller, the answer is also getting smaller. So these fractions that are really, really close to 0 will start going like this and gradually getting bigger, making a bit of a curve. And the same thing out this side. All right, so the correct way to join up these three dots is to draw a line that curves up and through them and continues in both directions. Okay, because as the fraction gets smaller, so too does the corresponding y value. All right. Now, this is a little bit interesting for a number of reasons because of this point in the middle here, how it sort of levels off at 0 and then starts rising past and before 0. So this point in here is called a point of inflection, and it's where that behavior happens, where it rises, levels, and then keeps rising past there. All right. It's different to a quadratic, which has a turning point where it rises, levels, and then goes back the other way. A point of inflection keeps going in the same direction as what it started in. All right. So that's the basic form of a cubic, x cubed. All right. Now, this is how to move it around, just for like quadratics. This is horizontal translation, vertical translation, and dilation, just like for cubics. All right. So when we're talking about turning point form, it's not a turning point, it's a point of inflection. All right. And this location is given by HK, whatever that is. Okay, so for this one here, H and K were 0, 0, and you can see that this is where the point of inflection is for this one. All right, so if you've been asked to sketch the graph of this one, all you need to know is where the important points are on this graph. So this one, these H and K values here give you a point of inflection, which are at 2, 4, so we can mark that 2 units across, 4 units up. So the same basic shape will take place, and you just need to know then where it goes through the x-axis, which we can do by setting the y value at 0. So 0 equals x minus 2 cubed plus 4, minus 4 equals x minus 2 cubed. Now don't get excited by the minus 4 on the left hand side there, because a cube root means you're allowed to have the negatives. So the cube root of 4 equals x minus 2, and then the cube root of minus 4 plus 2 equals x. So this value here is that value. We don't need to simplify it beyond there. You just have to say 2 plus the cube root of negative 4. The y-intercept we can set equal to x being 0, so 0 minus 2 is minus 2, minus 2 cubed is minus 8, minus 8 plus 4 is minus 4. So this location here is at minus 4. So we've got the location of the turning point, which is 2, 4. We've got the location of the x-intercept, and we have the location of the y-intercept, which is 0 minus 4. And then we've just put caps on the arrows in line with our maximal domain, which is, of course, R. Alright, now the last thing we'll look at before I get you to go and practice this is inverses of x cubed. So here's a graph of the red one being x cubed, the green line being the y equals x, which is the 45-degree line. And I've hidden the graph of the inverse, so I'm going to show you how you can look at it and what it will turn into. So we can pretty quickly understand that we need to sketch the reflection. So this top section will look something like that. This middle section here will look something like that, then that. Oops. I'll just get rid of that. So you can see here that continuously it's looking like that. Bottom section is going out there. Alright, so the blue line is going to be the inverse. Alright, now you can, if you just look at the right hand half from 0 onwards, you can see that it bears some resemblance to a cube root function, which is what the inverse does in fact turn into. Oops. So to do that algebraically, I'll show you. So we'll take y equals x cubed, we'll swap the x and the y, and you notice that you have to get rid of the cube, which turns into a cube root function, just like a square root. A quadratic turned into a square root function, a cube turns into a cube root function, and it has most of the same properties as a square root function. Alright, so algebraically, cubes turn into cube roots, and you can do that using reflections or the algebra, which you do need to know how to do. If you're asked to sketch one, you would just follow the same steps as you need to do to find the x-intercept, y-intercept, and whatever other points of inflection you need. Important to note, this center part here is not quite a point of inflection because it doesn't rise, then keep going round. Rise, then level off, then keep going up. It sort of levels off, then rises, then levels off again. Alright, so this, on the cube root function, that's not a point of inflection. Alright, so if we've been asked to sketch this one, we know that the center part is there. Alright, so we need to find out the x-intercept, so we'll set y equal to 0. So x minus 1 cube root. You should remember that this fractional power is the same as a cube root. So I'll put 2 across there. X minus 1 cube root. To get rid of a cube root, we cube things. So there's 8 equals x minus 1. Add 1 to both sides. 9 equals x. So that's the coordinate point of 9, 0. Then to find the y-intercept, we'd set x equal to 0. So 0 minus 1 cube root minus 2. So this is going to be minus 1, not a minus sign there, cube root minus 2. The cube root of minus 1 is in fact minus 1, because minus 1 times minus 1 times minus 1 is minus 1. So that's minus 1 minus 2, which equals minus 3. So the y-intercept is at 0, minus 3. Alright, so now I've got my points that I need to graph it. On my Cartesian plane, I'd mark those points, so one of them will be out here at 9, 0, one of them will be down here at 0, 3, not 9, 0. There. And then to sketch, it will look something like this. All right, you're not going to be expected to sketch it very well, depending on your scale of your graph. All right, you notice that the middle part of that should be at 1 minus 2. So 1 minus 2. So I could have drawn it a little bit further over here like this. But again, because it's not a point of inflection, strictly speaking, we don't label it in there, okay? So just keep in mind, to graph cube root functions, you'll need to know the x and y intercepts, and you don't need to label the point of inflection